This video is part 4 of Chapter 12, Tests of Statistical Significance for PSY 222, Research Methods in the Psychological Sciences. We finished up part 3 talking about using ANOVA to test for effects in studies where you have 3 or more groups. We hadn't yet talked about effect size, though. Effect size for studies where you have 3 or more groups is what we want to know is we want some measure of the size of the effect. So we're going to try and come up with a comparable measure to what was described for effect size in our 2-group comparisons. One of the most popular of these is eta squared, and eta squared it is calculated based on information that you can find readily in the summary table when you conduct your F-test. The ANOVA table provides you with the basic information that's required for the eta squared test. What the eta squared value does, it gives you a proportion of variance in scores, the individual participant scores that are due to the independent variable manipulation or the group assignment in a natural group setting. The larger the effect size, the way we describe that is the effect of the independent variable, quote unquote, explains more of the differences in the participant's performance than would be an effect that is a smaller size. The ANOVA, the effect size measure, is, as I said before, the eta squared value. And if you followed my tutorials for your Pallant homework and also my demo for the ANOVA that I did for the semester project, it's difficult to interpret, and I'm glad that Pallant explains this. It's difficult to interpret just based on the printout exactly what you've got in terms of an effect size measure, because the output gives you several different kinds and doesn't use the language that's exactly the same as what is used in your Shaughnessy text. But let's look at eta squared. Eta squared is, conceptually, you take the sum of squares between the groups and divide that by the total sum of squares. So conceptually what you're looking at is the variability between groups, that's the effect, and then the total variability, the total sum of squares, as the denominator. Now, if we're getting more technical in our definition, we have the F value from our table that we've calculated. We have the degrees of freedom that are associated with the effect. We have the F value again that times the DF effect, and then you add to that the degrees of freedom for the error in the study. What you're given is a standardized measure then of the size of your effect. It's similar to Cohen's D in terms of logic. So Cohen's F, if we want to use a similar thing to Cohen's D, we'll use this particular measure of effect size. Unlike Cohen's D gives you the effect size in terms of mean differences, so differences between 2 means. Cohen's F gives you the effect size based more on dispersion, so dispersion of the scores within a group of means. So both Cohen's D and Cohen's F tell you the effect standard that's in a standardized form, and it allows you to, in addition to your significance testing result, it gives you an additional way of describing the magnitude of the effect. Now, F is calculated using eta squared. So if you refer back to the last slide where we talked about what eta squared is and how it's calculated, F is determined in a standardized form So you have the eta squared divided by 1 minus eta squared, and then you take the square root of that value to give you the standardized Cohen's F. Interpreting Cohen's F, like we had with Cohen's D, we have some limits. So you have to have an F of at least 0.1 to be declared a small effect. Medium effects are 0.25 at a minimum, and large effects at a 0.4 at a minimum. Now, how do we assess the power? So how do we do a power assessment for independent groups designs with 3 or more groups? Once you know the effect size, you can get an estimate of power based on your sample size and degrees of freedom that are connected to the between groups effect in the F ratio. And all of that information is in the output table, so the ANOVA table, the F table in SPSS. Once you've got, learning about the power numbers, the assessment of power after the fact, it can be helpful, especially if you have a non-significant hypothesis test. So if on your NHST, you have a result where P is greater than 0.05, and therefore you have a non-significant result. The power analysis can help you to determine whether that might be due to your N being insufficient. And what you can do then is you can state, given the assessment of the power of the test, that it's likely that increasing the number of subjects would have had an effect in terms of how the statistics play themselves out. As with our discussion earlier, power in a statistical test is typically going to go up as your sample size increases. In multiple group experiments, another way that we can talk about our results is by looking at the confidence intervals. What we want to do is look at the pattern and the means by making some estimates of what the population means should be like, or are most likely to be like, and we're going to calculate just by convention a 95% confidence interval. And in a way, this is you're able to say, I've got this population mean. What is the likely range of scores that would include the population parameter from which this sample was drawn? What we can use confidence intervals for is to help us think about probable differences among population means that our sample means are supposed to be representing. These kinds of decisions, we're doing this because we want to be fairly sure that the means we have, so you have a mean for group 1, a mean for group 2, a mean for group 3, and so on. If there's a difference between those means, we would like to be able to say that those means represent, with a fair degree of confidence, 3 different populations. So if the confidence intervals for the means overlap too much, that suggests that they are not in fact different populations, they are the same population, and therefore whatever mean differences you're seeing are probably more likely due to error than they are to an actual meaningful effect. So what we're looking for is the degree to which the confidence intervals for the groups overlap. If they do, how much are they overlapping? Generally speaking, the less overlap, the better in terms of effects. Now, the width of the confidence interval tells you something about how precise your guesses are about your means representing your population. If they're very wide, you're not as precise. If they're fairly narrow, you're given more precision about your judgment. Now, I screenshotted this image from your text. It's the formula for how the confidence intervals are calculated. I just wanted you to note that they're connected to the mean for the group, the error, n, and you figure in, the critical value of t as a part of this whole picture. Now SPSS does this for you, so when you get your test results, you're going to be given confidence intervals for your groups when you do the post hoc analyses, and that's how you can look at the degree to which your groups are actually overlapping and versus the degree to which they're separate. The null hypothesis significance test for comparing the pairs of means in these designs. So you've done an F test to look at the overall, that's in the ANOVA. Now you need to break it down to paired comparisons. So we're interested in not just are there any differences among my groups, we want to know that, but we really want to know what's the pattern and which groups differ from which other groups. So we have to make comparisons between pairs of scores, or pairs of means, rather. One approach to doing this is to do follow-up t-tests. And these are a specific kind of t-tests that are based on what's called a pooled variance estimate. I've grabbed an image of the t formula. So you've got, for a pair of means, so let's say in my version of the semester project, I've got the youngest group and the oldest group of participants. And I've got the mean difference up here on the top, my numerator. I've got mean square error, 1 over the n for group 1, 1 over the n for group 2, and then the calculation of the square root ends up with a t value. Now in your output on SPSS, it's going to give you the t value and the significance value for your paired comparison. When you make that selection of a Tukey post hoc, that's essentially what you're getting. The variance estimate in the formula uses information from all of the groups in your experiment. So this MS error, it's not just your two groups, but it's the whole experiment. So it's taking into consideration not just the two groups that you're comparing, but all of the error for the entire sample. And then, in the context of all of these groups, this pair, and then assessing whether or not the means are significantly different from one another. When we're comparing the means, we can also ask some questions using Cohen's d. You can calculate that for comparisons between two means as a result of that t-test. And once you've got the t value, you can calculate the Cohen's d. When we're using a t-test to make decisions like this, we do adopt a specific probability. By convention, it's usually 0.05. Now, as your authors have pointed out more than once, the exact probability is important, and that's why journal publishers have moved in the direction of requiring that authors report the exact value as opposed to the inexact, less than or greater than information when it's appropriate. The lower the exact probability, the greater the likelihood. As with most of the ways we phrase this for NHST, the greater the likelihood that an exact replication would allow you to reject the null. Now we're going to shift gears and talk about repeated measures ANOVAs. You understand the logic of the dependent t-test, where basically it's repeated measures, but it's only one comparison that you're making. So here you take the general logic that we've been talking about already, but you're using a repeated measures analysis of variance instead, because you have more than two time periods that are being compared, or more than one measurement times being compared. So before you begin the analysis of variance for what's called a complete repeated measures design, you look at your summary scores, you look at your descriptive statistics, and those are calculated for each condition of the experiment. And they represent summarizing the performance for each condition. One of my SCEs last year, they had a repeated measures design where they took measures of heart rate variability, among other dependent variables, at 3 separate points in time. It was all within subjects, although there were 2 different orders, but it was within subjects. Every subject had their heart rate variability calculated at 3 points in time. So we wanted to calculate their heart rate variability at each of those 3 points in time. The primary way that ANOVA for repeated measures differs from other kinds of ANOVA analyses is in terms of the way error variation is calculated. Sometimes this is called residual variation. Basically, the residual variation is what's left over after systematic variation. That's the variation due to the independent variable, and due to individual differences in the subjects is taken out. And that's why they call it residual. So it's what's left over. So when we're summarizing repeated measures data, the first step is you want to look at each individual's performance in each condition. And then you're going to calculate descriptive statistics at each point in time, so across participants in each of the conditions. So you end up having every individual has a score at time 1, a score at time 2, a score at time 3, for example. And you'll end up calculating a mean for all of your participants at time 1, a mean at time 2, a mean at time 3. The null for the omnibus test is that the population means at each time period or each interval is the same. Now the next step is that you need to estimate the error variation, as well as the systematic variation, and you might recognize this as the numerator from an F test in terms of the statistical formula. We also, though, we need to estimate just error variation by itself. In a repeated measures design, and just as a reminder from the last slide, what we're looking at is wanting to be able to describe the differences in how the conditions affect the different participants. So it's kind of like you're looking at in these several points in time, each participant is given the same test. What is the degree to which, as individuals, they respond differently at these different points in time? And that becomes the residual variation. Now, your authors present you with a concrete example, and in these tables that they give you in the chapter, and again, I encourage you, I put these pictures in the presentations to remind you to look at these sections of the text carefully. So in the top image, you have the data matrix, which basically is a table of individual scores. And you have different interval lengths in this particular study. Then the bottom table is the output, is the SPSS output, with degrees of freedom, sum of squares, mean squared, F value, and P value in it. You want to kind of look, just to give yourself some familiarity with your data, you're looking at, these are the individual scores, this is the mean for the group at that interval, These are the individual scores, and notice the variability in those individual scores. So you have, one individual here has much higher scores than the other individuals. You have a couple of individuals who seem to be lower than the other individuals. You want to familiarize yourself with those individual scores. Then you look at the means, the averages at each interval. And what the repeated measures test is going to do is to say, for these participants in these different interval lengths, do these means differ? And then the test this is the omnibus test, then tells us, yep, somewhere in that pile of means, there's differences. And then you have to interpret where they are. Now, an additional kind of test that we frequently run is something called a two-factor analysis of variance. Sometimes it's called a two-way analysis of variance. You'll notice in your Pallant text, you have a chapter on one-way ANOVA, and then you have a chapter called two-way mixed with in between, which is more complicated than it needs to be. It's essentially an ANOVA where you have two independent variables. And you're interested in finding out, do they interact with one another in terms of changing or affecting the scores on either one independent or one dependent variable or several. We often call these factorial designs. And what we will use to test for effects is F-tests, ANOVA tests, where we look at a combination of what are called main effects and interaction effects. So when you have two independent variables in your design and you're interested in whether they interact, remember this study that I described to you that I conducted where I had two independent variables. I had program type, a control TV show, a crime drama with violent content but no mental health content, and a crime drama with violent content and psychiatric labeling. That's my first independent variable, program type. The second independent variable was whether or not there were public service announcements that advocated mental health awareness. So I've got two independent variables. Now, I'm interested in, does the type of program by itself, regardless of whether there are public service announcements or not, does the program type matter? That would be a main effect for A. I'm also interested, regardless of what people are watching, is there an effect for the presence of public service announcements? That would be the main effect of B. And I also want to know what combination of these two variables, what kind of effects does that produce? And one of my findings was you get the lowest levels of stigma, things like violence ratings. You get the lowest level of violence ratings when people watch the control television show and when they saw public service announcements. In the other conditions, watching public service announcements didn't decrease stigma when they were watching the worst kind of show. Now, two-factor ANOVAs or two-way ANOVAs, or as Pallant puts it, two-way with in-between analyses, are going to happen in a variety of ways. Sometimes you have two manipulated independent variables and you're doing a random groups design, so you're assigning people to different conditions of both independent variables. You could have IVs that are in a natural groups design. So in your semester project database, you could take age in 3 groups and sex, where you have 2 groups, and do basically a factorial testing for differences on dependent variables like life satisfaction to see if there's an interaction between age and sex on your dependent variable. And that's what they mean by natural groups design. In some studies, you have one independent variable that's a natural groups variable and another independent variable that is randomly assigned. So there's all kinds of mixtures that are possible here. A straight up random groups design, a design where you have a factorial and the groups are defined by natural characteristics of the individuals, or a mixture of the two. Now, how the ANOVA is done, you will have, as is the case with all ANOVA tests, you're going to have an omnibus test that's going to tell you first if there's an interaction. And Padlet makes this really clear for you in your homework. With the complex designs, you first have to ask the question, is there an interaction? Because the answer to that question is going to determine how you interpret the main effects, the separate effects of your two independent variables in the analysis. A simple main effect is, as I described the example to you earlier, when you're just looking at the independent variables in isolation. So a simple main effect is, as your authors put it, the effect of one independent variable at only one level of a second independent variable. There's overall main effects and there's simple main effects. Simple main effects, let's say you're using the semester project data set, you have age in 3 groups and you have males versus females. If I only look at the males, is there a main effect for age? If I only look at the females, is there a main effect for age? Then you can have an overall main effect. You can collapse across the sex variable and have just a main effect for age, regardless of sex. When you have an independent variable that has 3 or more levels, comparisons of means can be used to think about the simple main effects where you're comparing 2 at a time. So let's say you're looking at males only and looking at the age differences, and you have a significant simple main effect there. You're going to then ask which age groups are different from which age groups among the male participants. You know, before I leave that, you can also collapse across gender groups. So you can collapse across males and females and ask the same question. We often, though, we want to segment them out and look at them separately. You can look at confidence interval information as a means of helping you to draw conclusions about the nature of the differences you might be seeing in the means. And it also helps you to be much more precise in terms of how you talk about any differences you find. Now, if you have an interaction effect, so the first test, and I'm glad that in your Pallant text she so carefully goes through all of the complicated output that is present for these kinds of analyses in SPSS, because it can be extraordinarily confusing. So first you want to look at the interaction, and if you have an interaction effect, then you look at looking at the main effects is going to be more challenging. So if you have a significant interaction effect, then you really need to look at the effects of your first independent variable by separating out the groups defined by your second one. So let's go back to the age groupings, age in 3 groups, and your second independent variable is sex. If I have a significant interaction effect on my test result, then I don't want to collapse across the groups, because that would be misleading in terms of interpreting the means. I have to separate them by group and interpret them separately. And that's why, Shaughnessy is saying here, if you want to look at you want to interpret the source of the interaction, then you have to look at the main effects in their simple form, not in their collapsed form, and then make comparisons 2 by 2 of your means. After you look at the simple main effects and you do the analyses there, then you can look at the overall main effects of the independent variables when you're collapsing across your other DV. And then you use confidence intervals around those group means to give you some sense of the degree of overlap in that you would be estimating for your population means. As usual, you want a smaller interval around that sample mean because that's going to represent a more precise estimate of the population. Now, what if you have no interaction effect? If there's no interaction and you get your omnibus test and it says you have a non-significant interaction effect, then you go straight to your main effects and look at them collapsed across your other dependent variable. So if I, when I looked at age and sex, although I would have to fact check that, but let's go with the hypothetical. If I had 3 age groups and then sex broken down into 2 groups, let's say that I found a non-significant interaction effect, then I could directly interpret the main effect for age and the separate main effect for sex on my dependent variables. I would then compare means 2 at a time to look at the source of any significant main effect and construct the confidence intervals to have an assessment of precision. Now, how do you report the results when you don't have an interaction effect? What you include when you're giving your description of these findings, you're going to get the descriptive statistics for your independent variable groups on your dependent variables. Typically, we do this in the form of a table, sometimes a figure. If you have a small enough number of means, you can do it in the text. You also are expected to provide effect size measures. When you report the results of the ANOVA itself, you need to provide information about the significance test of the interaction effect and of the main effects. Simple main effects and post hocs would be presented if they're appropriate. And if you have a non-significant effect, providing a power analysis is useful for determining why. You still, though, you have to give a verbal description of whatever effects might be there. Means plots can help you because they help you to visualize, although as Pallant notes in her text, you should be careful in the way you interpret those means plots because they do tend to make differences between groups appear greater than they actually are. And that concludes part 4 for chapter 12.